Hi students, welcome to HSC Chemistry and Module 8, Applying Chemical Ideas. This is video number 7. We're going to be looking in this video at colorimetry. So what we've looked at so far is a number of qualitative techniques for identifying the presence of ions in solution, and then we've looked at some ways of extending or changing the way that we do some of those procedures in order to turn those qualitative measures into quantitative ones. So precipitation reactions, which just identify the color or the presence of a particular ion through the formation of a precipitate, can be extended into more of a quantitative process by either collecting and drying and weighing those precipitates or through the process of precipitation titration. But what about flame testing? Is there a way that we can use techniques based on the different spectra in order to turn something that was basically a qualitative identification of ions or colored solutions into something that's a little bit more quantifiable? And of course there is. In fact, there is a number of techniques that are based on the spectra of different atoms. And one of those, of course, we've got one of these not limited to, so we need to make sure we look at a number of these different types of techniques. But one of the ways of determining the concentration of colored species or metal ions in aqueous solution is to use the technique of colorimetry. Again, if you've got a colorimeter available, and we've been struggling to get hold of one, but we will be able to at least demonstrate this process, give you a chance to have a very quick look at the process of colorimetry, and we'll just quickly look at some of the theory or background behind colorimetry in this video. So basically this is it. For solutions that are colored, what that means, if we sort of very briefly look at our understanding of light, what we know is that white light strikes any surface. If that surface is fully reflective, then all of the light is going to bounce off that surface. We can even calculate things like the angles, and you'll see that as white light. Of course, if some wavelengths are absorbed and some are reflected, then you will not see all of those wavelengths recombining to form white light, but you may actually see different colors separating out. So we know that there are different colors based on which colors or which parts of the visible component of the electromagnetic spectrum reach our eyes, and how our eyes obviously interpret those as different colors. So different solutions are going to either absorb or transmit components of the electromagnetic spectrum as light passes through them. So you can see here, it's just very quickly, the diagram on the right is effectively white light. So this is light which contains all of the colors of the rainbow, effectively from red to violet. And as it passes through this purple solution, you can see that some of those wavelengths are absorbed, and when they're absorbed, they basically leave behind a black region, a black band. Others are transmitted or allowed to pass straight through, and so those are the colors that we tend to see. The combination of wavelengths is what adds together to produce the different colors that we see in the solution. Now obviously these two solutions over here on the left, so if I call this solution 1 and this solution 2, you can see just by the color of these solutions that they can't be the same concentration. Solution 1 seems much darker than solution 2. It would be reasonable for us to conclude that solution 1 has a higher concentration of some type of ion. We might suggest that this is potassium permanganate, but we would have to do tests on that, or you could just read it underneath in order to confirm that that was the case. But we could definitely see that the darker solution is one that obviously has a much higher concentration of ions in it, And so therefore there should be some way that we can make some comparisons about how much of the light is absorbed, how much of the light is transmitted, and to be able to convert that into a way of being able to make some conclusions about the concentration of a particular solution. And this is effectively what colorimetry is all about. If you think about the fact that we could have a colorless solution in which we can measure different wavelengths of light passing through that solution, and then we have a second solution which has a color, and again we pass the same light of the same wavelength through there, and then what we can do is make a comparison. So if this is A and this is B, we can make a comparison between A and B and see that any difference between them must be associated with the ions that are in solution that are absorbing that that extra energy associated with particular wavelengths of light within the visible spectrum. Another thing that we can do with colorimetry and indeed something that is very often practiced with this sorts of technique, and something we'll also see for something like atomic absorption spectroscopy or AAS in a later video, is that we can make up a number of known solutions. So what we do is we calibrate an ion. So in this case, we know that the colors of most solutions are attributable to the cations. So in this case, it would be reasonable to assume that the purple color has something to do with the presence of potassium ions in the solution, and maybe that the potassium ion concentration is affecting the depth of color that we see. And so that's something that we could investigate. The best way to do that is to make up a series of known solutions. And that's known concentration. So we know that a number of different solutions have a certain concentration which we have measured. We can make up these solutions, we can dilute solutions, we know how to do that. So we can have a series of from A, B, C, D, E, a series of concentrations. What will happen is that we then look at what reading we get for each of these when we pass them through, when we put them into the colorimeter. And that's going to pass light through them. It's going to give us an absorbance. And so we're going to end up with a series of values that are going to correspond to different concentrations. What this allows us to do is to draw a graph. So here's an example of a calibration curve. It's a calibration curve that has a series of data points already on it. And you can see these points shown along this graph. What's happened is that we've looked at these data points and we've said we can draw a line of best fit between these points. And so that's the blue line on this graph. You can see now that we have a relationship between the absorbance on the y-axis and the concentration on the x-axis. And again, we can do this for any substance, but we can't just calibrate our colorimeter once and then expect it's going to be the same for all sorts of different ions. Each time you use a different ion, you need to calibrate against that particular ion. Nevertheless, once we have a calibration curve like this, what we can do is to then have an unknown, and let's say we measure an unknown. Of course, the solution must contain the same cation, and let's say that we measured that to be have an absorbance of 0.6. So let's say the absorbance is equal to 0.6. So what we do is we look at where 0.6 is on our graph, and we're going to interpolate. So we're going to run that across, and then we're going to run that down, and it's going to give us, therefore, the concentration is going to be 600 parts per million. So using a colorimeter requires you to set up a calibration curve first. You need a number of known solutions with known concentrations. You then need to measure the absorbance. You need to record those in your table, plot them on a graph, and then to interpolate them from the graph. Now, this is an interpolation. One of the things that we will look at is we want to try as much as possible to avoid extrapolation. Because even if the curve for the small values, range of values that we look at starts nice and straight, it may curve at some point at higher concentrations. And of course, if we've only got a small portion of that line, we can't assume that it's just going to go on forever. We need to make sure that we have additional data if we're going to do that. So if we find that we get an absorbance value that lies outside of the range of values that we've tested in constructing our calibration curve, then we're going to have to add additional known concentrations to see what happens to the graph beyond those values that we've already measured. This is basically the technique of colorimetry. It's a very quick overview, but something I think that hopefully will give you at least a starting point so that when you go and use this technique in the laboratory, you'll have a little bit more of an idea of what you're doing and why you're doing it. And of course, forming these sorts of calibration curves is a very important skill and one of the things that we will often test in chemistry. Thanks for watching and good luck.